Hello everyone, welcome to my tutorial with the title Beyond Bug Hunting, Verification Coverage from Safety to Certification. My name is Nicolae Tusinschi, Product Specialist Design Verification at OneSpin Solutions, and I will be happy to guide you through this tutorial in this presentation. First, we at OneSpin, our goal is to provide certified IC integrity verification solutions. And the solutions are targeting all steps in the SOC, ASIC, or FPGA verification flow from the design, from the early step of designing up to the integration and then later the implementation itself. We play and we target several aspects of the integrity verification, IC integrity verification, and main focus is functional correctness, safety, trust, and security. So now that let me introduce to what we are going to present in this tutorial. So first we're gonna touch on what are the verification challenges and more verification flow challenges, to be more precise, how we tackle these challenges with the mutation-based coverage solution called OneSpin 360 Quantify. And then we are touching on the integration problem, where the mutation-based coverage metrics are integrated with other metrics. And then we introduce the OneSpin 360 portable coverage solution from OneSpin that is solving this problem. In the end, we are concluding, and you feel free to ask questions. So we'll be happily answer your questions. All right, so jumping into the verification flow challenges. So in this picture, you can see how a classic verification loop looks like. So everything starts from requirements, from which a team sets a verification plan, having its verification goals for all the requirements. Then, based on this verification plan, engineers are building test benches to test the features. These test benches are the run and debug. After the run and debug, there is an assess of the metrics, and then later it goes to the sign off of the verification. But so when starting in the nowadays, there is multiple technologies that are part of the same verification loop, and from a classic verification loop where the simulation was used, it is transformed into hybrid verification loop, and you need to plan for both simulation and formal for verification plan, and you also need to take into account that you need to annotate the plan with simulation and formal results. Building the test bench, this activity can be split, but can be a hybrid activity. So people who are doing simulation can do only simulation, or people who are doing formal can do only formal, or they can do both. So there is need to set up this environment. Of course, the run and debug is a step that is run individually. So both simulation and formal have this process, have this step in the process and we are running in their own environment, then this, after the runs and the debug is complete, the coverage is collected, and someone needs to assess this coverage from simulation and formula. And this is not a very easy task. That's why assessing the quality of verification has a tremendous importance. So basically, if you don't measure, you don't know. And the main question of when you measure is, yeah, you can measure, but when are you done? So coming to answering the question, you need to break down this big question into smaller one. So first is, what part of the design has been exercised by my assertions and cover properties? Second, which is of very good and not very easy to achieve, is to achieve an answer is, have I written good quality assertions? Also, which parts of the design have been checked by my assertions? On top of it, there are two more questions that you will need to answer. Is, are all specified functions implemented? And this translates back to the requirements and verification plan step. And same, one more question that you need to answer before you can answer if you're done with your verification is if your specified functions are verified. So first three questions of these are covered by the coverage mutation-based analysis with OneSpin 360 Quantify. The last two, which we don't cover in this presentation, are covered by the gap-free verification, which is actually answering the questions if your specified functions are implemented and if all specified functions are verified. So, but what is this quantify meant to do? So, quantify is actually targeting two aspects. One is the coverage and the other one is bug hunting. So both coverage and bug hunting are important. Of course, having 100% coverage with bugs in the design is unacceptable, and later this, if you are ignorant and having coverage, 100% coverage, but you still have bugs, this is gonna bite you badly later in the process. One good aspect and that you need to progress quickly in the verification process is that the extraction of this coverage matrix should be quick and easy, and the report data must be meaningful. So far, the formal coverage analysis that is out there, it's inconclusive. So we all know that there is the cone of influence, the proof core techniques. So mainly, let's analyze one by one. We're looking at the cone of influence. Of course, you have some inputs to the design, outputs to the design. Here you specify an assertion that you set to monitor an output, for example, and then the cone of influence is extracted. So cone of influence is very over optimistic, and much logic that is in this cone of influence is not relevant for the assertion proof. Of course, the proof engines try to trim the irrelevant logic. And our technology is the proof core, So basically, this is a trained cone of influence. It's over optimistic, but the most important part and the most is that it's very engine dependent. Also, the results are hard to interpret, need support from the vendor. There is mismatch with abstraction level of other forms of coverage and makes review process much harder. You can explore more in the link of this tutorial from DVCon U.S. 2018. Okay, what is this actually, this mutation-based coverage analysis that is solving the problem? So it is a multi-dimensional coverage view. So when we mention the mutation coverage is you're looking at two different views. One is the answering the question, has the statement been activated? And the idea behind this is if a statement cannot be activated, exercised during verification, it can break a check. So basically, if you have a check, but this you cannot activate it, you can exercise this check will not fail. So this is measuring the quality of the stimuli. Another view is if has the answering the question has the statement been detected? And the idea behind this is if a statement is modified and activated, some checks should fail. Would any check fail if the statement cannot be reached? And it measures the quality of the checkers. So having these two views that targets the activation and the detection, this is becoming much stronger and is measuring the quality and the of the stimuli and the quality of the checkers. So yeah, this quantity and quality of the mutation coverage is assessing the quality of verification by providing a quantitative metric. Structural coverage measures the quantity, so the activation and detection coverage provides quantitative assessment. Functional coverage is measuring the quality. So the assertion coverage provides qualitative assessment. How does this looks from coming to the regular flow used by verification engineers very heavily only OneSpin? This mutation coverage use model is then becomes an iterative flow, and this can be used actually by designers and verification engineers for iterative sign-offs. So you're planning, you're running test benches, you're collecting metrics, something is not covered, you go back, you re-edit your verification plan, build more test benches, need more runs, and so on and so on. Eventually this loop will close and the sign-off will happen. So this is an iterative sign-off flow for bug hunting and 100% coverage. So yeah, OneSpin 360 Quantify is the solution that has under the hood the mutation-based coverage analysis, has this two-dimensional view, and let's understand the verification coverage that you're getting to reach the sign-off. So what Quantify gives you as a solution, it gives you a precise measure of progress and coverage improvement. It is very easy to use. It's a push button solution that does the analysis of your formal test bench and answers the questions of how good are your stimuli and how good are your checkers. It has a high return on investment, and you can sign off with confidence, with 0 post-production bugs. But let's target one by one. So for the precise measure of progress and coverage, so basically it gives you an accurate and reproducible results by mutation analysis. It's fast in execution runtime by model-based fault injection and optimized parallel engines. So it doesn't do a mutation at a time. It does parallel mutations, and this increases the performance. Does a precise mapping to the source code by source location tracking. As I pointed out already, there is no setup time. It's a push button tool integration solution. Fast result inspection by integrated browsable annotated source view. So there is a nice annotated source view where you can see what is covered and what is not covered. Actually, there is no extra installation, so it's part of the DV verify. So you need the same license to run assertions, and same line, and on top of it you run the coverage analysis. And yeah, improved execution and predictability in verification projects by focusing effort. It's a solution that is reliable to identify verification gaps and blind spots by highlighting over-constraining, dead code, and redundant code. The results from the metrics collected by the Quantify app can be integrated with third-party verification planning, tracking, and simulation code coverage solutions for coverage closure using the portable coverage, which we're going to talk later in this presentation. But let's understand and let's see what coverage results are there in Quantify. So first of all, we classify them, and the first category is the activation coverage. This actually is important to identify which parts of a design are dead and which parts are over-constrained. As the code is dead or over-constrained, one cannot control it. So, and this actually targets the dead code, which is introduced by the designers, and later on, dead code can be introduced by the verification engineers by over-constraining. So the coverage solution makes the difference between these two, and the effect is the same. The code is dead, but it comes to two different sources. Then we have the detection coverage, and this is classified in two. So you have the undetected, which means that mutation didn't detect, is not detected by any assertion, and covered. So basically, when a mutation is exercised, the assertion, at least one assertion was failed, and in the result, mutation detected by at least one assertion, and classify this location as covered. So yeah, it's important to assess the quality of assertions, and the question is, have we observed all the design signals? Do we have quality assertions? Can be answered with this metrics result. On top of that, the solution has the capability to identify additional coverage results. So it's identifying the redundant code. The verification code is separately from the designer code, so the verification logic is kept separately from RTL in terms of annotation, and then the excluded by the user code is annotated and is excluded from the coverage analysis. So the excluded won't be, it will make the closure faster. Sorry. So when I said that it's a highly annotated source view, so 2 years ago we presented a tutorial on bug using Quantify for bug hunting. Feel free to review the. You can find the links on the OneSpin website. But the source view, it looks like this. So basically, what you're seeing here is an annotated source view where there is no locations covered at all. So initially, if someone would run Quantify without writing any assertion, it will get this view where it's clearly highlights in red that all locations are not covered, and one would need to write assertions and in an iterative process run Quantify in order to get this covered. There is a nice dashboard that informs the user on how much is covered, how much is uncovered in terms of statements and branch coverage. You can see the assertions that are used for this analysis, the source files here, then you have the excluded code overview, and there is some more additional information that users can find in this dashboard, also like what options are used to run Quantify, etc. When one writes enough assertions, so meaning he's covering one is covering the verification plan, then the goal would be to get 100% coverage and to get such a view where all locations are highlighted in green, meaning that there is no over constraints, no design bugs, all design statements are observed, quality of assertion is good, and the most important is you are ready to sign off. But now once you are getting this, your desired metric score, how does this play a role in how can you use this advanced coverage analysis to achieve to speed up your certification? So as you may know, there is a broad safety standard, functional safety standard landscape, and OneSpin is actually active across many of these standards. So here is a graph on how these standards are classified. So you have the aerospace, the avionics standards on the side. So the more famous DO254 for aerospace defense, and then there is the IEC 61508, which incorporates a set of substandards, and this includes the process control, the machine tooling, the nuclear power, medical, railway, and one of the standards where the OneSpin is active is, of course, the automotive, the famous ISO 26262. Exactly. But how? Let's focus a bit first on the DO254 and how can OneSpin coverage solutions actually help and make this flow more rigorous. So the DO254 development flow overview. So this is the core of the RTCA. So it comes with several sections, the recommendations that users need to keep and to follow in the development. Planning, then you have the design itself, the hardware design process, from requirements capture, conceptual state, detailed design, implementation, production transitions. And the most important part here is that this implementation, requirements capture, implementation are tightly, you can see the connection between the planning, the validation and verification process, configuration management. Of course, not all of them are related to verification, but planning, validation and verification, implementation. These are tightly connected. So how can formal verification make this flow more rigorous? There is a process where you do the design code analysis, and you need to ensure that correct RTL upfront is produced. How can you achieve that? So ignore the last part of the flow where it's more about implementation and ending up on this synthesis implementation, focusing on the RTL design. So what do we need to do for the certification? You will need to do requirement tracing and verification, code coverage closure for simulation, and code coverage for elemental analysis. First, so you need to get reachable code coverage. So OneSpin helps you to get an immediate feedback of dead code issues. So even in Quantify, not using the dead code checkers, in Quantify, you can have a view of what is dead and also what is over constrained. Here is an example of quantitative analysis of simulation completeness in DO254. You have a small state casements where the case binary 1-1 is controlled by an acknowledged signal. And the problem is here is that there is insufficient code coverage during DO254 elemental analysis prevent certification. An example, some branch is never executed because acknowledge cannot be asserted in this context. Solution to this is you do an automatic formal inspection using DVinspect. Automatically identifies reachability. So automatically with formal you can prove that code can be documented or fixed to achieve certificate. For example. Another example would be the FSM state and transition coverage. So, of course, this is a bit shifting from the mutation-based analysis, but this is an early step in the process. So, automatically you need to find and extract the FSMs from RTL, and this is easily done with the DVinspect FSM analysis, which checks the coverage for all FSM states and transitions in DUT, and reports the number of cycles from reset to reach a state transition. You can see this represented by the digit between the braces. This is the looping state, reset state, etc. And it shows you in such a nice matrix where you can see the transitions state to state. Yeah, so this reports also the statement that cannot be covered. So looking back at the elemental analysis in the DO254 verification flows, the code coverage for it, it starts from the DAL IB designs governed by the DO254 Appendix B, which has several methods including elemental analysis. And for piece elemental analysis, you need to have code coverage to ensure all design code is exercised. In this case, we have statement coverage, all statements executed, branch coverage, all branches reached, FSM coverage, all states and transition reached, toggle coverage, no signals get stuck, condition coverage, focused expression coverage. So quantify is covering this part. FSM is covered by DVInspect. Toggle covered by DVInspect. Condition focused by functional verification. So this is all can be covered with formal OneSpin mutation-based coverage solution for quantify and DVInspect on top of it. So yeah, OneSpin 360 DV, formal powered inspection of RTL code. When to use it? During the RTL development process, assess the quality of third-party IPs or legacy modules, code coverage closure for elemental analysis, DAL-AB. The benefits of using it. It detects corner case design errors. Low noise with very intuitive debug environment. So you don't have a lot of noise. You don't need to run thousands of cycles in order to monitor. It has a robust and efficient analysis of code coverage holes. With the metrics view for FSM or the dead code analysis from the dead code checkers, or the nicely highlighted source view produced by the quantify. And yes, it also provides tool assessment, so independent assessment through review of results. Certification, it's a consideration on potential strategy and benefits. So the tool assessment, so the independent assessment through overlapping methods, remaining gate level simulations and onboard testing, or verification credits. Credit achieved with RTL simulation-based verification of requirements might be ported across implementation steps to post-layout netlist. Reduce net need for gate level simulations, which is very tremendous and effort-consuming job. So OneSpin for the DO254 has produced a tool qualification kit, which contains the tool qualification guidelines, development process certificate. So development process and testing tool documentation is certified by the authority. It comes with a tool testing package, and it has a PHAC and HVP ready. And you can apply, configure, and integrate in your DO254 project to get the certification DAL-AB. Another standard, since we focused only on DO254, are the family of IEC 61508, especially the automotive, which is a very well-established standard for the automotive industry in Germany and worldwide. So what are these automotive applications? So X-by-wire, ADAS, everyone needs to meet the safety measures. So you need to do requirement tracing, hard soft error detection and control. There is a set of references in this slide to actually projects where the OneSpin verification solution, the coverage solutions, has been used to achieve these certifications. But as you've seen, both standards, the DO254, the ISO 262, both are looking to do a rigorous verification and requirement tracing. And when it comes to requirement tracing and coverage metrics, these are becoming of paramount importance. Requirement tracing are broken usually in features that for each features, after the features are implemented, each feature comes with a verification goal, and each verification goal then has can have a single methodology, or it can have multiple methodologies. As we may know, today verification is not a single, as I pointed out already, it's a hybrid. So verification is simulation and formal, and they just work fine together. So formal is working fine with simulation. Simulation targets some specific applications, areas where formal is not so good at, and vice versa. Formal is very good in identifying bugs where the simulation needs very difficult ways to come with these input patterns in order to trigger this specific bug. One important aspect in requirement tracing and all of this coverage metrics analysis for certification is actually the coverage databases. Because these are coming from different sources, they need to be aggregated. And yeah, so same as for DO254, for ISO 26222, OneSpin has passed the audit and factory inspection from TÜV Süd. It comes with provides a tool qualification kit that does the tool documentation and safety manual, safety certificate plus report, and you can use it and ready to apply to the following ISO 262 TCL3 and the family that are in this category. So as I pointed out, these coverage databases that are coming from different sources, these are triggering the so-called integration problem. And the integration problem is, as you've seen in this flow, that the planning is done for simulation formal. Same time, you need to measure the assertion quality and to integrate this simulation formal coverage and to analyze unreachable assertions. So there is a couple of missing pieces that OneSpin 360 portable coverage are solving. And actually, how the flow looks like. So basically, you are having design specification that comes into verification planner. Basically, here is where the verification goals are stated. Then simulation test benches are developed based on the verification plan. Assertion test benches, formal assertion test benches are developed, and these are tested against the design itself. So before this, an early inspection of analysis with the so-called CCA app is solving the problem of unreachable code. So basically, simulator should not spend time on what is formally dead, and I say formally dead, validated dead. Same time, assertions are proven, and the proof results, the assertions need to be annotated into verification planner together with the simulation results. Same time, there is the VCI app, which is measuring the coverage metrics from the quantify. And these are annotated together with the simulation coverage in the same coverage viewer that can be separate
have the
or can
overview
be
of
the same.
Open integration. Let's see what challenges the solution is solving. This brings us to the coverage closure accelerator. What is this actually doing? So the coverage closure accelerator does an analysis of design to find unreachable coverage targets and provides this information to other tools in the flow. So in general, the targets that are identified to be unreachable in OneSpin via quantify or via the dead code checks analysis are provided in forms of some exclusions to the other tools in flow, such that the other tools don't spend time and effort on trying to reach these targets. So yeah, the verification teams knows that the wasting time to trying to hit unreachable targets is very consuming. It can save many simulation cycles. The coverage viewers ignores the unreachable targets when calculate the metrics. Therefore, these metrics are getting higher if the coverage closure analysis is being used. So the flow with the OneSpin is the following. So you have the DUT that is undergoing some simulation test bench and also some formal analysis. Therefore, the dead code check analysis or quantify, of course, is producing this reachability formal analysis database that are then passed through the CCA app, the Coverage Closure Accelerator app. The coverage exclusions are generated and are provided back to the simulation environment, which are taking this into account and helps to reach the desired metric score. The second challenge is solved by the verification coverage integration app. So this is targeting both simulation formal coverage to integrate. So it enables the integration of coverage from simulation runs and from formal runs. It's part of the OneSpin's portable coverage solution. And in general, the results, the metrics, the coverage metrics, structural coverage metrics generated with quantify mutation analysis are run through the verification coverage integration app, and the coverage databases are generated. Therefore, these databases that are generated with quantify can be used to do the side-by-side analysis with simulation coverage to identify the goals that are still missing. How does it look like? So this on the left side we have the quantify reports. We've seen this dashboard. Now we have the coverage highlighted view in OneSpin of the quantify. So you can see the red, the green, and all these results are translated into the simulation. So here I have a simulator view, coverage viewer, where you can see that the green is annotated to be green, the uncovered is annotated to be excluded. The fourth challenge that is being solved with, and the third challenge that is being solved is solved by the verification planning integration, and this targets the challenge of having functional coverage from simulation and formal runs. This is also part of the portable coverage solution. and works in the following ways. So you have the verification planning, and then targets, goals for this verification plan are running. Some of them are targeted with simulation, and some of them are targeted with formal. Therefore, the formal targets are running OneSpin by creating assertions, cover properties, and the results from OneSpin, when they are run through the VPI app through the verification planning integration app, are back annotated into the verification plan, resulting in such a nice green annotated verification plan. Here is an example from the Questa coverage report where we have this verification plan, and then using the annotation, you can see that here I have some, in the test when I had some targets that should be targeted by simulation, and I have a 6 here, which is the OneSpin formal verification, and this is actually the assertions that are part of this 6 OneSpin formal verification here. So yeah, from such a verification plan, you can end up in a Questa coverage report where you have the formal result from OneSpin, the functional result annotated here. Here is the same for VCS, where you have the same verification plan I used for Questa. It is just annotated, and you can see here the formal results by bit controller are annotated. Here is the source. Here is the assertion pass and fail. So again, reiterating through the open integration flow. So you have start from a design specification. You develop this verification plan that has structural coverage metrics goals and have the functional metric goals. The design is common for both methodologies. Engineers are developing and test benches and formal test benches, which are run through the simulation and through the property checker and quantify. OneSpin does the analysis on the DUT, so no need for any simulation test benches to generate these coverage closure exclusion files that are fed into the simulator, such that the simulator doesn't spend time on trying to reach unreachable targets. Therefore, the formal test bench is running through the property checker and quantify. The result is you get functional coverage metrics and structural coverage metrics. These are undergoing through the app's VPI, respectively VCI, that are later fed. Results from these apps are used into verification plan to annotate the functional metrics, or the results from the VCI app are fed into the coverage viewer to view the coverage goals, to identify the coverage goals. So the summary of this, we have like formal verification, where the verification coverage integration app, cover closure accelerator app, verification planning app, integration app, and quantify this model-based part of the solution. It can be used with simulation verification optionally. Reportable coverage, the goals is to integrate formal and simulation coverage, accelerate coverage acceleration, accelerate coverage closure, and track formal results in verification plan. You can use any simulator planning tool. And what you get is a coverage database, coverage closure, verification sign-off, and you can annotate this coverage database to the verification plan. So summing up what we have been walking through, so there is a couple of takeaways. So, and the benefit of using quantify for bug hunting and for safety and certification is that you have a designer bring up, so you have these automated checks, that reachability analysis, find design bugs as you bring up design, redundant code, and designer asserts. These are designer targeted. So basically designers are gonna use in the early phase this, then there's a lot of benefit that one can achieve using the automated checks and the coverage solution checks from OneSpin. Therefore, the verification quality and metrics. So metrics indicate gaps, and quantify identifies missing or low quality assertions, identify accidental over constraining, which is very difficult to spot in simulation. It's a push button solution, so run frequently and track progress. If you developed some pieces, just give it a try, leave it to run, get quick feedback, and adjust to reach their early return on investment. Portable coverage integrates the formal simulation coverage, accelerate coverage closure, and track formal coverage results into verification. You can use any simulator, coverage database, verification planning tool. Compliance with functional safety standards is challenging, so requirement tracing in this case is crucial. So the coverage provides evidence of verification, and tool assessment or qualification might be required. OneSpin provides high quality tool qualification kits for multiple safety standards. I have prepared some references and further reading, so if you're interested, go through these white papers, conference papers, and watch some videos on the topic. And again, we at OneSpin provide certified IC integrity verification solutions to develop functional, correct, safe, secure, and trusted integrated circuits. We target all the steps in the verification flow from design up